Module 1, Introduction to Artificial Intelligence. Objective, understand the basics of AI, its history, and its impact on various industries. Definition of AI. What is AI? AI involves creating systems that can perform tasks that typically require human intelligence, such as visual perception, speech recognition, decision-making, and language translation. Key components. AI consists of machine learning, natural language processing, robotics, and other fields. History of AI. Milestones. 1950s. Alan Turing's work in the Turing test. 1956. Dartmouth Conference, where AI was formally born. 1980s. Rise of expert systems. 2000s. Advancements in machine learning and deep learning. Evolution. How AI has progressed from simple rule-based systems to complex algorithms and deep learning models. Types of AI. Narrow AI. AI that is designed for a specific task, such as facial recognition. General AI. Hypothetical AI that possesses general cognitive abilities. Superintelligent AI. AI that surpasses human intelligence, currently speculative. AI versus machine learning versus deep learning. AI, broad concept of machines being able to carry out tasks in a way that we would consider smart. Machine learning, ML, a subset of AI that involves training algorithms to learn patterns from data. Deep learning, DL, a subset of ML that uses neural networks with many layers. Applications of AI, healthcare, diagnostics, personalized treatment plans, finance, fraud detection, algorithmic trading, automotive, self-driving cars, retail, recommendation systems, inventory management. Theory, philosophical foundations, Turing test, a test of a machine's ability to exhibit intelligent behavior. Chinese room argument, a thought experiment by John Searle to argue against the notion that a computer running a program can have a mind or understand. Examples, case studies, healthcare, IBM Watson for oncology. Finance, algorithmic trading systems by companies like Goldman Sachs. Interactive session, impact discussion, debating the future implications of AI on jobs, privacy, and ethics. Module 2, Machine Learning Fundamentals. Objective, learn the basics of machine learning, including key algorithms and their applications. Introduction to machine learning. What is ML? The study of algorithms that improve their performance at some task with experience. How it works, using data to train models that can make predictions or decisions without being explicitly programmed to perform the task. Types of machine learning. Supervised learning, learning from labeled data, such as classification and regression. Unsupervised learning, learning from unlabeled data, such as clustering and association. Reinforcement learning, learning by interacting with an environment to maximize cumulative reward. Key algorithms. Linear regression, predicting a continuous target variable based on linear relationships between the target and input features. Logistic regression, classification algorithm used to predict binary outcomes. Decision trees, tree-like model used for classification and regression tasks. Clustering algorithms, k-means, hierarchical clustering for grouping similar data points. Theory, mathematics of machine learning, linear algebra, vectors, matrices, and their operations. Probability and statistics, concepts like mean, variance, probability distributions, and Bayes' theorem. Algorithmic theory, how algorithms work, detailed explanation of the mathematical principles behind each algorithm. Examples, hands-on projects, linear regression model, implementing a simple linear regression model to predict housing prices. Clustering, grouping customer data using k-means clustering. Real-world applications, spam detection, using logistic regression to classify emails as spam or not. Customer segmentation, using clustering algorithms for market segmentation. Module 3, Deep Learning and Neural Networks. Objective, understand the principles of deep learning and how neural networks operate. Introduction to neural networks, basics of neurons. Neurons as the basic units of a neural network. Activation functions, functions like sigmoid, ReLU that determine the output of a neuron. Network architectures, feed-forward, convolutional, and recurrent neural networks. Deep learning frameworks, TensorFlow, an open-source library developed by Google for numerical computation and deep learning. Keras, a high-level API for building and training deep learning models. PyTorch, an open-source machine learning library developed by Facebook's AI Research Lab. Convolutional neural networks, CNNs, for image recognition, how CNNs are structured to recognize and classify images. Recurrent neural networks, RNNs, for sequential data, how RNNs handle sequences of data, making them suitable for time series prediction and language modeling. Theory, backpropagation, learning in neural networks, the mechanism by which neural networks learn, involving the propagation of error gradients backward through the network to update weights. Advanced architectures, ResNet, residual networks that help in training very deep networks. LSTM, long short-term memory networks designed to remember information for long periods. Transformer models, state-of-the-art models for handling sequential data without the need for recurrent connections. Examples, hands-on projects, implementing a CNN, building a CNN for image classification using the MNIST dataset. RNN for time series prediction, using an RNN to predict future values in a time series dataset. Interactive session, NLP and computer vision, exploring practical applications of deep learning models in tasks like language translation and object detection. Module 4, natural language processing, NLP. Objective, learn how AI processes and understands human language. Basics of NLP, tokenization, splitting text into tokens. Stemming and lemmatization, reducing words to their root forms. Text representation, bag of words, simple method to represent text data as a set of tokens. TF-IDF, term frequency inverse document frequency, a statistical measure used to evaluate the importance of a word in a document. Word embeddings, vector representations of words, such as word2vec, glove. NLP tasks, sentiment analysis, determining the sentiment expressed in a piece of text. Language translation, translating text from one language to another. Chatbots, building conversational agents. Theory, linguistic theory, syntax, the arrangement of words to create meaningful sentences. Semantics, the meaning of words and sentences. Pragmatics, the context-driven aspects of meaning. Advanced models, BERT, bidirectional encoder representations from transformers, a powerful pre-trained language model. GPT, generative pre-trained transformer, a model known for generating coherent and contextually relevant text. Examples, hands-on projects. Sentiment analysis tool, building a tool to analyze the sentiment of movie reviews. Simple chatbot, creating a chatbot using NLP libraries. Real-world applications, customer service, how NLP is used in automated customer service and support. Content recommendation, using NLP to recommend relevant content to users. Module 5, computer vision. Objective, explore how AI interprets and processes visual data. Introduction to computer vision, key concepts, understanding images and color spaces, challenges, variability in lighting, occlusion, and viewpoint changes. Image processing techniques, filtering, techniques like blurring and sharpening. Edge detection, methods like Sobel and Canny edge detectors. Color space conversion, converting between RGB, HSV, and other color spaces. Object detection and recognition, using models, YOLO, you only look once, and SSD, single-shot multi-box detector, for real-time object detection. Theory, image processing, theory, how computers interpret images, understanding digital image representation and manipulation. Advanced topics, semantic segmentation, classifying each pixel in an image into a category. Facial recognition, techniques used for recognizing and verifying human faces. Examples, hands-on projects. Object detection, implementing object detection using pre-trained YOLO models. Image classification, building an image classifier using CNNs. Interactive session, ethical considerations, discussing the ethical implications of using computer vision in surveillance and privacy. Module 6, reinforcement learning. Objective, understand the fundamentals of reinforcement learning and its applications. Introduction to reinforcement learning, key concepts, agents, environments, states, actions, rewards. Terminology, policies, value functions, and Q functions. RL algorithms, Q learning, model-free reinforcement learning algorithm. Deep Q networks, DQN, combining Q learning with deep learning. Policy gradients, algorithms that optimize the policy directly. Applications of RL, game playing, AI agents learning to play games like chess, Go, and Atari games. Robotics, teaching robots to perform tasks through trial and error. Autonomous systems, applications in self-driving cars and drones. Theory, Markov decision processes, MDPs, theoretical foundation. Framework for modeling decision-making in environments where outcomes are partly random and partly under the control of a decision-maker. Value and policy iteration, learning optimal policies, techniques to find the best policy that maximizes the cumulative reward. Examples, hands-on projects, training an agent, using OpenAI Gym to train an agent to play a simple game. Real-world applications, exploring how RL is used in finance for trading strategies. Interactive session, Ethics in RL, discussing the implications of autonomous systems making decisions in critical situations.